out the questions as we're going through the PowerPoint. So what is force? So force is anything that is a push or a pull. It's an interaction that it changes the motion. So when you apply a force, we're looking to change the direction of the object if at all possible. Examples of force. So the obvious, just pushing and pulling of things, like those are forces. There are also some that we'll see today, forces due to air resistance. So when things are moving through the air, it's applying a certain type of friction. We have friction from, for example, just the floor, friction from movement, tires on a road are producing friction. We also have the force of gravity. Gravity is the force that's holding us down. It's pulling us towards the surface of the earth. Gravity is different depending on the planet you're on, because gravity is in relation to the mass of an object or how big something is. So those are all some types of forces. So you should have filled out what a force is. You could even do number 5 and give an example of a force. So the equation for force, you talked about last week, force is equal to the mass of the object times the acceleration. So sometimes if the object's just falling through the air, that's going to be acceleration from gravity. If it's from you pushing the object or pulling the object, it's going to be the acceleration you use when you're moving that object through the space. So to change force, question?
Where do we get
Did I miss you? Sorry about that. So to change force, the effective force, we need to either change the mass, the acceleration, or both. So if we add more mass in our equation here, so we see force equals mass times acceleration. If we make m bigger, we add mass to our object, our force is going to have to be bigger to move it. So it takes more force to move bigger objects. Same thing if our acceleration is more, if we want to move something faster, it's going to require more force. Force is measured in newtons. So newtons, we're thinking of like Sir Isaac Newton when we think of these newtons. Sir Isaac Newton, he discovered a lot of the forces deal with gravity, so he got to choose the measure of unit for force. Like we talked about, weight is an example of force. So your weight, what you think about when you think of weight is probably like, how much do I weigh? Like 100 pounds, 200 pounds, something like that. However, weight's a little bit different because scientifically, your weight is due to the acceleration of gravity. So how much the earth pulls down on you is your weight. So a lot of people misuse it. If you say my weight is such and such, weight's actually measured in newtons. You're giving your mass when you measure in things like pounds and kilograms.
Whoa.
So this is just kind of showing an example how your weight would change on different planets. So your mass would stay the same. You're not changing size as you go to different planets. But planets with larger planets with more mass, they're going to have a greater pull of gravity. So your weight would be, for example, if you're on Earth and you weigh 63.5 kilograms or 140 pounds, that's your weight in newtons. If you go to something like Jupiter, much bigger planet, on Jupiter you weigh 355 pounds. On the sun, you weigh almost 4,000 pounds. So your weight changes a lot, but your mass stays the same, so you're not going to look any different. I mean, except for you burn alive, of course, but.
How would you find that weight on the sun? Who went there?
Yeah, that's a great question.
Measured that?
So how can you do that? Because it's all based off of the mass of the planet. They have equations because of gravity where we can figure out approximately the mass of Earth, like how much Earth weighs. We can do the same thing for the sun. They do this by, it's some complex science by saying, okay, how big is the sun in diameter? How dense is the sun? And they kind of do some of the experimentation to develop. Obviously, it's not an exact, like, we know to the exact kilogram how much the sun weighs, but they can get a pretty good approximation. So how we're going to apply all of this, we're using the equation of force, and we're turning it into work. So work is not like school work, okay, where you're dealing with this science work. So not like that example of work. This is the example we're looking for, is work in physics. The equation for work is, it's force, like we've talked about, times a distance. So we want to travel a certain distance to do work. If you don't travel any distance, you're not doing any work. So even though it might feel like if you push on that wall as hard as you can, put a lot of force in, but the wall doesn't move, you didn't do any work, okay? So for work to be done, distance has to be traveled. And we're going to see that in our experiment, in our demonstration today. So today's demonstration, what we're going to use, we're going to use some spring scales. This might be a new tool for you guys. What spring scales do, so we have a spring inside. It's very similar to how a scale works that you're finding your weight on, for example, like at a doctor's office or at home. So we have one side that says grams, and one with a G, and one side with an N for newtons. You want to use the side for newtons, because we want to use our force, right, is measured in newtons. So the more pull there is on our spring scale, you can read down, it starts at 0 all the way to 2.5 newtons for pulling a lot. So we're going to see how our work changes as we're dragging objects up a ramp. We're going to drag them without a ramp, and we're going to change the mass of objects.
Is it hard to pull?
No, it's not hard to pull at all. So we have pretty light objects. We have objects with a small mass, so you can see the change pretty easily. So we're seeing how force and work change. We're going to change the slope of our ramp. We're going to change the distance that we travel, and we're going to change the mass of the object. Okay? So I want you guys to think, make predictions. How is changing my mass going to affect my force? How is changing my mass going to affect my work? Okay, you have a couple prediction questions on that front page. So go ahead and write out predictions. How does changing the slope of the ramp affect the required force and work? Why are these things happening? So we want to think, if I add more mass, what's going to happen to my force? If I add more mass, what's going to happen to my work being done? Same thing, if I change my slope of my ramp, is it going to make it easier? Is it going to make it more difficult? Think what you know about inclined planes, what you've been learning with your simple machines. So those are the predictions I want you to make. So go ahead and jot some of those down on your paper where it's asking for your predictions, and explain why you think so. Okay, it's okay to be wrong. There's no right or wrong answers in your predictions. You're not going to lose points for a wrong prediction, but just try to think logically why this is happening. Yes? So you only have the one, you only have how changing the ramp will affect the force and y on your sheet, but I want you to think through in your head for the other predictions. So it's in the middle under the lab part where it says predict. So that's the prediction you're writing on your paper. The other predictions I just want you to kind of think about in your head, and then we're going to see if you were correct or not. So what we're going to do, I'm going to partner you guys up. You're going to have a group, you're going to have 2 objects with a mass. You're going to have 1 spring scale. You're going to have 1 ramp. Okay? You're going to follow these guidelines here. We're going to attach the spring scale to your object. You're going to record the force from a flat surface. So we're going to put the spring scale in the object. We're going to pull it on a flat surface. Then we're going to pull it up the ramp. Then we're going to use both of your masses together. You're going to see how that changes. And then we're going to calculate the work. On the back page of this, we have our lab guidelines here, okay? So you're going to have the force of our ramp. I have it measured out already for you. You can see on our ramp we have a 0.2 meters, 0.4 meters, 0.6 meters. So you're going to pull your object up the ramp. You're going to record the force from our spring scale at each of these lines here. So each ramp has that. We want our ramp to be about 15 centimeters tall. So I have some rulers for you guys. You can use stacks of books. You can set it on the edge of a desk if you need to, but try to make it about 15 centimeters tall for the first part. And then we're going to readjust it. And I'll pull this up so you can see it a little better here. And then we're going to make it so it's a taller ramp. So we're going to do 2 different sizes of our ramps. We're going to test it on the flat ground. We're going to do 2 different masses. So you're going to do just your object, and you're going to pull your and your partner's object. Okay? So I'll talk through this again once we kind of get everything passed out. So go ahead, part number 2, 4, 6, 8, 10, 11. So I'll have one group of 3. So why don't you 3 guys go together? You 2 ladies back here. Let's go you 2. Matt and Josiah, and then you 2 ladies, okay? So each group gets a ruler. Each group's going to get a board. There you go, gentlemen. Oh, too far. Okay?